Hello, here's an engineering economics video about annuities, particularly sinking funds and capital recovery accounts. So we're talking about the letter A, annuities. Remember, an annuity is an amount, a series of payments either going into the company or out of the company. The cash flow can go either way. A series of payments that are the same amount for successive periods. So the same amount happened repetitive times, either being deposited into an account to save up for a large equipment purchase, a wedding, a down payment on a house, to have a fund to close a facility like a nuclear power plant or a landfill at the end of its life. You want some large amount of money at the end of a time period, and then you're thinking about making periodic contributions to that account to save for that future large expense. So that's one example of an annuity. The kind of annuity called a sinking fund is an interest-bearing account into which a fixed sum is deposited at regular intervals. And we designate that by the letter A. One type of annuity is a sinking fund. We'll do an example of that first and then go on to another type. A equals F, the future value that you need, times this horrible formula, so complicated formula. So I prefer to use the interest factor tables where the amount of the annuity is the future sum that you're looking for times a factor from the interest tables, right? Find A given F, I given I, and given N number of time periods. All right, let's look at an example. Your goal is to purchase a home in 4 years, and you know you'll need a $50,000 payment at that time. How much do you need to save and deposit into a 7% interest-bearing account each year so that at the end of 4 years, there's our N, you have a $50,000 sum in that account? That would be F, and I is 7%. So here's a cash flow diagram. Let's plot out the problem. Time 0 right now, nothing happens. We're going to assume this is a regular annuity in which the payments are made, the deposits are made into the account at the end of each year. And that's what we're looking for, the amount of the annuity. That would be the same amount going into the account. So I put it as down arrows because you're taking cash out of your savings and putting it into another savings. So cash out, and then I'm just going to put it up cash in. The future value, what you'll need towards your home purchase, is $50,000. So that's what we're looking for at an I of 7%. So we set it up, annuity amount that we're looking for equals 50,000 future value times a factor from the interest table, and then the annual amount works out to $11,260. That's a regular annuity, meaning you would deposit that amount at the end of each year. If it were an annuity due, the timing would be that you would be depositing that money at the beginning of each year, right? Giving you one more interest period to earn interest. So if you deposit $11,260 at the end of each year for 4 years, earning interest at 7%, you'll end up with $50,000 at the end of the 4-year time period. You can put the down payment on the house. Using Excel to find the annuity payment required each year in a sinking fund scenario, you would type into a cell in Excel equals PMT for payment, the interest rate, the years, a 0, and then the future value. The answer will come out as a negative number, but you just reverse the sign and realize that that is the amount you need to deposit into the account each year in order to reach your $50,000 at the end of the 4 years. All right, the other kind of annuity payment stream that we'll be calculating today is find A given P. So now we're going to be finding the amount of the annuity, but given the present value. So it's called a capital recovery factor. That's find A, annuity, given present value, an interest rate, and a time frame. Here's the formula here, if you care to use that. I prefer, again, to use the interest factor tables, where we take the given present value amount times some capital recovery factor from the interest factor tables in the find A given P column on that particular interest table. Okay. So here's an example. A capital recovery factor is used when you have a present value and you're looking at what would be the equivalent lump sum payment, or not lump sum, but payments over time a series of fixed payments over time that would equal that initial present value. For instance, if you have a loan, and you make equal annual payments to pay off that loan, that's what we're looking for. How much is that annuity? How much is the loan payoff amount that you'd make monthly or annually? Let's look at an example. Here we have borrowed $21,061.82 for college tuition. And the payoff plan is to pay it off over 5 years in equal annual installments. We'll just start with annual. And the annual interest rate is 6%. So the approach first is to recognize what factors you're given in the problem. The $21,000, the amount of the loan today, is a present value. N is 5 years. And our interest rate, I, is also on annual terms. And so we would recognize that as a capital recovery factor. Find A, how much is the equal annual payments in order to pay off that loan in 5 payments over 5 years. So the approach is to use our capital recovery factor, find A, given P of 21,061 times a factor on the 6% interest table. Find A given P, 6% for 5 years annual interest rate, and so our N is in number of years as well. There's the factor. So our annuity amount, do that math, works out to a magic even $5,000 to be paid at the end of each year. Let's actually draw a timeline to show that. $5,000 payment at the end of each year will pay off that loan in 5 years. So I'm going to write the loan amount as a positive here, $21,061.82 at time 0. That is our P. And then we're going to make annual payments, 1, 2, 3, 4, 5, at the end of each year. And our interest rate is 6%. And how much is the A? There's an A each year here. How much? There's a timeline showing the cash flows for this capital recovery problem. And we've gone through the math here. Find A, given P, how much are each of these A's? 5,000. So interpret that. What that means then is that if you make loan payoff amounts 5,000 at the end of year 1, 5,000 at the end of year 2, 5,000 at the end of year 3, 4, and 5, that adds up to $25,000 of cash that you're paying out, but you're just paying off a $21,000 loan. So the other 4,000-ish difference between adding up these cash flow payments and the initial present value, the difference between those is the interest that you have paid on that loan during the 5 years. Capital recovery. And so here's the Excel formula for that. Enter into a cell equals payment, parentheses, I, N, and P. I is entered just as the full number. 5 is the N, 5 years. And then in the present value or future value, any of these in Excel, when you're entering dollar amounts, don't put a comma in, just enter the full number here of the present value. Push enter, and Excel will return $5,000. Okay, here's a related concept. Again, we'll be finding A, but in this case, we're going to be finding the average annualized payment over a period of time, either given F or given P. So let's look at this. This is called Equal Uniform Annual Cost, EUAC, and we use that to work with outflows of cash, right? Cash outflows are costs, and we want to come up with what's the average annual cost of a project, or Equal Uniform Annual Benefits, EUAB, and that is for cash inflows are benefits, right? So EUAC and EUAB are both finding the annuity for any series of cash flows. They can be different amounts each year. And it is cool because you're just trying to find the average annual cost or benefit of owning a machine. Maybe there's an initial cost. Maybe there's some cash inflows from contribution margin from running that asset or that machine for a while. There are cash outflows for maintenance and repairs and kind of things like that by using this piece of equipment. Maybe there's a salvage value where you can sell the asset at the end of its life. So there's a cash inflow the proceeds from selling the asset at the end, or maybe there's a disposal cost at the end of the asset's life and it's a cash outflow at the end. And EUAB and EUAC give you the average annual cost to own that asset, each annual cost or benefit each year, averaged over the asset's entire life. So it's a pretty cool way to analyze different machines and different investments when you're looking at what's the average annual cost or benefit each year under each machine option or each option that you're looking at. Of course, you would choose the one, from a financial standpoint, you would choose the one with the lowest average annual cost or the one with the highest average annualized benefit, right? So let's see how we do that. Here's a cash flow diagram in general terms. When you're looking at find A given a future value at the end, you're taking all these cash flows, inflows and outflows, different amounts over the life of the asset, and coming up with one average annual amount. Or we can also do the same thing if we're given a present value and we're looking to find the equivalent annualized amount, find A given P. Both of these, you'll be given an interest rate and an N. The decision rule then is to pick the option with the highest benefit and the lowest cost. Sometimes these are computed and then shown in the form of a ratio where we want the benefits to exceed the cost. If you divide them like that, turn it into a ratio, you want it to be greater than 1. That's the financial metric to analyze alternate investment options using annualized EUAB or EUAC. Okay, let's look at an example of trying to decide what would be the average annual cost of owning a particular machine that has an initial cost, annual operating outflows, or annual operating inflows, cash generated from running that investment, and then a salvage value or proceeds from selling that asset at the end of its life. In this example, the initial cost is $80,000, which includes the cost of the machine, freight, sales tax, and setup costs like laying a cement pad, installing water lines, electricity lines, and so forth. All that is added together to come up with a total estimate of initial cost. Then we have salvage value, what the machine can be sold for at the end of its life. That's cash proceeds realized upon selling that asset at the end of its life. And here we have annual operating costs of $18,000. The machine will last for 20 years and we'll use an interest rate of 10%. So I've put those amounts in pink here on our cash flow diagram. The initial cost of the machine, $80,000, is already in terms of P, present value. The operating costs are stated as an annual amount of $18,000. That already is in terms of A. We're trying to find A for this entire series of cash flows. Those annual operating costs already are in terms of A, right? The salvage value proceeds that we can sell that machine for at the end of its life is a future value, right? So we want to turn that future value into A and turn the initial cost into an A, and annual operating costs already are in terms of A. Then we can get an average annual cost or benefit of running this machine for its entire 20-year life. So to solve that, we say A equals, we're looking for A for this entire stream of cash flows, $80,000 initial cost, which is in P, times a factor from the interest table in the find A given P column, 10% interest table for 20 years, that factor, times the initial purchase price, minus $20,000. Now, why did I do minus? Here on this, I'm choosing to use $80,000 as a positive number. That happens to be a cash outflow. So if I'm saying outflows are positive, then inflows have to be the opposite sign or a negative. You could go either way with those. Treat the costs as negatives and the inflows as positives, but as long as they have opposite signs, it doesn't really matter. So since this is a cost that's a positive, I'm going to take this $20,000 future value and treat it as a negative because it's cash coming in. So $20,000 times a factor from the 10% interest table in the find A given F column, 10%, your 20, row 20, times that factor times 20,000, and then plus $18,000. Why that? Well, again, our operating costs already are in terms of A, and it's a cost, so it's a plus, and there's the amount 18,000. So I pick up these factors and multiply by the numbers next to them. I get 9,400 is the annuity annualized amount of that initial cost, minus $350 is the average annualized salvage value in 20 years. Spread out over those 20 years, it averages out to $350 per year. Plus 18,000 is our annual operating cost. Net those together, and I get EUAC of $27,050. Now, how do I know that's a cost? Because I was treating costs as positives, and the answer comes out to positive, so that is a cost. Let's interpret that. $27,050 is the average annual cost to operate this machine, buy it, operate it, and sell it. All of those cash flows averaged out to as if it were one annual amount each year for 20 years. So that's not how the actual cash flows go, right? Because the cash flows go per our diagram. But averaging everything out turns out to be an annualized amount of $27,050. So what good is that? Well, we can take, that's the average annual cost for this machine. We could compare that to other alternate assets or investments that would do the same job and pick the one with the lowest average annual cost or the highest average annual benefit, right? So it's useful to compare two or more options. Given different cash flows, you can use this for different lengths of time. This one was 20 years. You could use this technique to compare to a 10-year asset or any other life because you're analyzing it on a per year basis. What is the average annual cost?